We will start our next topic, that is colloids. Now, what are colloids? These are some examples of our colloids which we used in day-to-day life. These are foams. This is milk, fog and smoke. This is detergent, blood, aerogel, paints and cosmetics. Now, from these examples, we will come to know that there is a solvent and a solute mixed in it, and which are not completely miscible, that we can see uh, the solute and solvents. So these types of the solutions are known as colloids. Now next is colloidal dispersion. Dispersed system consists of particulate matter dispersed phase, which is known as the particulate matter is known as dispersed phase, and dispersion medium, that is continuous medium. And classification on of dispersed system according to particle size is molecular dispersion, colloidal dispersion and coarse dispersion. Molecular dispersion is less than 1 micron meter. Particles undergo rapid diffusion, example O2 and glucose. Colloidal dispersion is 1 micrometer to 500 micrometer. Very slow diffusion, example colloidal silver salt. Now, coarse dispersion is greater than 500 micrometer and it don't diffuse, example suspension and emulsion. Now, colloidal dispersions. Molecular dispersion, particles invisible in electron microscope pass through semi-permeable membrane and filter paper. Colloidal dispersions, particles resolved by electron microscope pass through filter paper but not pass through semi-permeable membrane. Coarse dispersion, particles are visible under ordinary microscope, do not pass through filter paper or semi-permeable membrane. Now, types of colloidal systems are according to the interaction between particles of dispersed phase and those of dispersion mediums. It is based on lyophilic, that is solvent loving, lyophobic, solvent hating, and association, that is amphiphilic. Next is sols, which are colloidal solutions. Dispersion medium is solvent. Dispersed phase is material or colloidal particles. The lyophilic colloids. Colloidal particles interact to an appreciable extent with the molecules of the dispersion medium, that is solvent loving, obtained simply by dissolving the material in the solvent due to the high affinity. Types of lyophilic colloids. According to the types of solvent, it is hydrophilic colloids and lipophilic colloids. Hydrophilic colloids have solvent water, example acacia insulin in water, and lipophilic colloids have solvent non-aqueous organic solvent, example rubber and polystyrene. So material that form lyophilic colloid in a certain solvent may not to do so in an another solvent. Example, acacia plus water gives lyophilic colloid. It is hydrophilic type. Acacia plus benzene is no lyophilic colloid formed. Next is lyophilic colloids. The dispersed phase does not precipitate easily. The sols are quite stable as the solute particles surrounded by the two stability factor. A. Negative or positive charge. B. Layer of solvent. If the dispersion medium is separated from the dispersed phase, the sol can also be reconstituted by the simple remixing with the dispersion medium. Hence, these sols are called as reversible sols. Now, lyophobic colloids. The colloids particles have very little or no attraction for the dispersion medium, that is solvent heating. Means the colloidal particles will not have any attraction to the dispersion medium, so they are solvent heating. Colloidal particles, inorganic particles, example gold, silver, sulfur. Dispersion medium will be water. These colloids are easily predicted on the addition of small amounts of electrolytes by heating or by shaking. less stable as the particles surrounded only with a layer of positive or negative charge. Once precipitated, this is not easy to reconstitute the sol simple mixing with the dispersion medium. Hence, these sols are called irreversible sols. Not obtained simply, that is need special method for separation. Means lyophobic colloids, if we mix silver particle in festivals like Holi, if we mix the color, it is inseparable. These are irreversible, so these examples are irreversible sols. If we mix the color for some time, if we shake the color bottle, the color mixes up with the water. But if we want to separate the color and water, it is impossible. So they are irreversible source. But the color and the water can be separated by another method of separations. Next is lyophobic colloids. Methods to prepare lyophobic colloids are dispersion methods. Coarse particles are reduced in size by ultrasonic generator, electric arc, or colloidal mill. Ultrasonic generator, dispersion achieved by high intensity UG at frequency more than 2000 cycles per second. Now electric arc involves production of an electric arc within the liquid and dispersion achieved by intense heat generated by the arc. So some metal of the electrodes dispersed as vapor then condensed to colloidal particle. A colloidal mill, material sheared between two rapidly rotating closed plates, low efficiency and reduce the size of the small proportion of particles only. This is electric arc. This is dispersion medium and this is ice. Next is condensation method. Material of subcolloidal dimension are caused to aggregate into particles with colloidal size range by change in solvent, chemical reaction. Now change in solvent. Change in solvent gives supersaturation form, then formation and growth of nuclei, colloidal system formation. Example, sulfur and alcohol in excess of water. Chemical reaction. Hydrogen sulfide on oxidation gives sulfur atom which gives sulfur salts. This is Br2 plus H2S gives sulfur plus 2HBr. HNO3 plus H2S gives H2O plus NO2 plus S. Ferric chloride plus water on hydrolysis give ferric oxide sol, that is red color. Hydrogen sulfide plus arsenious acid on double decomposition give arsenious sulfide sol. Association colloids. Certain molecules or ions termed as amphiphile, surface active agent, that is SAA, are characterized by two distinct regions of opposing solutions affinities within the same molecules or ions. Surfactants are amphiphilic, that is amphiphatic. These are surfactants. Hydrophilic head, they have hydrophilic head, that is water loving head, and hydrophobic tail. Hydrophobic means water hating or solvent hating. Association colloids. At low temperature, amphiphile exists separately subcolloidal site. At high temperature, form aggregates or micelles, 50 or more monomers, colloidal size. These are scheme of molecule of surfactants. This is hydrophilic head, hydrophobic tail. Surfactants arrange themselves on the water surface like a monolayer of molecules and inside it as micelles and membrane tied by their hydrophobic tail. As the cohesion of these molecules is interfered to that of the molecules of water, the surface tension of water is lowered. As we introduce the surfactants, it forms micelles in water and it reduces the surface tension of water. This is a layer of soap. See, layer of soapy water, the molecule of the surfactant arrange themselves with the head in the water and the tail outside it. Okay, so I have said that head is hydrophilic and tail is hydrophobic. Next is, see, association of colloids. These are micelles. How they are formed? The aggregate of hydrophobic tails forms the micelles. This is non-spherical micelles. This is vesicle. This is bilayer and this is reverse micelle. As with the lyophilic soles, formation of association colloid is spontaneous provided that the concentration of the amphiphile in solution exceeds the CMC, that is critical micelle concentration. Amphiphiles may be anionic, means surfactants may be anionic, that is lauryl sodium lauryl sulfate, example cationic, example is cetyl triethyl ammonium bromide. Non-ionic amphiphile, example polyoxyethylene lauryl ether. And ampholytic, that is zwitterionic, example dimethyl dodecyl aminio propane sulfonate. This comparison of properties of colloidal soles, their disperse phase, solvation, preparation, viscosity, effects of electrolyte. The lyophilic, that is solvent loving, lyophobic, solvent hating, and association. Large organic molecules lying within colloidal size, inorganic particles such as gold or silver. Aggregates of small organic molecules or ions whose size is below the colloidal size. What is solvation? Solvated. Lyophilic are solvated. Lyophobic are little in. And association are hydrophilic or lipophilic portion of the molecules is solvated depending on the medium. Preparation. Spontaneous by dissolving in solvent needs special procedure. Spontaneous when concentrated of amphiphile exceeds CMC. Viscosity. Viscosity increase as the concentration increases. At certain concentration, gel-sol gel formation not greatly increased due to unsolvation. And here is increased as concentration of amphiphile increases as micelles number increase and become asymmetric. Effect of electrolytes. Stable in presence of electrolytes. Desolvation and salting out in high concentration. Unstable due to neutralization of charge on particles. CMC is reduced and the salting out occurs at the high salt concentration. Now this is shape of the colloidal particles. The more extended the particle, the greater its specific surface and the greater the opportunity for attraction. The more we extend the particle, the greater will be its specific surface and greater the opportunity of attraction. Properties of colloids as flow sedimentation rate and OB are all affected by the shape of the particles. Purification of colloids. Why it is necessary to purify colloids? Many lyophobic soles contain more or less material in true solutions, which may be undesirable for any number of reasons. Example, electrolytic impurities cause the flocculation of the sole. How? Dialysis, electrodialysis and ultrafiltration. Now how we will filter it? Okay, with dialysis, electrodialysis or ultrafiltration method. Now what is dialysis? Depend on difference in size between colloidal particles and molecular particles impurities. Technique, use semi-permeable membrane, example colloidin, nitrocellulose or cellophane. Pore size of used semi-permeable membrane prevent passage of colloidal particles and permit passage of small molecules and ions impurities such as urea, glucose and sodium chloride to pass through. Okay, pore size of used semi-permeable membrane passage of colloidal particles passes small and impurities such as urea glucose. A type of dialysis equipment, that is needle dialyzer, at equilibrium the colloidal material is retained in compartment A while the subcolloidal material is distributed equally on both sides of the membrane. By continually removing the liquid in compartment B, it is possible to obtain colloidal material in A that is free from the subcolloidal contaminants. Over here, the explanation of that is given over here at start and at equilibrium. This is A, B, this is A and B. Okay. Next is the electrodialysis. And Electric potential may be used to increase the rate of movement of ionic impurities through a dialyzing membrane and so provide rapid purification. Now we will use an electric potential over here. Electrodialysis is carried out in three compartment vessel with electrodes. This is vessel with electrodes in the outer compartment containing water and the sole in the center compartment. This is outer compartment water and in middle is sole. Typical apparatus is shown in figure. Application of electric potential causes cations to migrate the negative electrode compartment and anions to move to the positive electrode compartment. If we apply electric field, the negative compartment will migrate to cations will migrate to negative electrode and anions will migrate to positive electrode compartment. In both of which running water ultimately removes the electrolyte. Now ultrafiltration. Apply pressure or suction to solvent and small particle forced across a membrane while colloidal particles are retained. Okay, the membrane must be supported on a sintered glass plate to prevent rupture due to high pressure. Pore size of the membrane can be increased by soaking in a solvent that causes swelling. Example, cellophane swell in zinc chloride solution. Colloidal nitrocellulose swell in alcohol. Artificial kidney machine. This is artificial kidney machine. Patient's blood arterial pass through cellophane coils. Ideal semi-permeable membrane for hemodialysis. Cellophane pass urea, glucose, electrolytes but do not pass plasma proteins and blood cells. Pure dialyzed blood enter the body again through a vein. Success of the artificial kidney machine depends on its ability to reduce blood urea. Cellophane coils are supported on a drum rotating the electrolyte solution, that is rinsing fluids. Now suit artificial kidney machine. Importance of rinsing solution are substance present in excess in blood, example urea, diffused from blood to the rinsing solution. Substance which are deficient in blood, example bicarbonate, diffused from the rinsing solution to blood. Substances which are present in normal amounts in bloods are kept unaltered, have the same concentration in both blood and rinsing solution. Pharmaceutical applications of colloidal silver iodide, silver chloride and silver protein are effective germicides and not cause irritation of ionic silver salts. Colloidal copper used in cancer. Colloidal gold is used as diagnostic agent. Colloidal mercury is used in syphilis. Association colloid are used to increase solubility and stability of certain compounds in aqueous and oily pharmaceutical preparation. Suit pharmaceutical applications of colloid. Efficiency of certain substance is increased when used in colloidal form due to large surface area. Example, efficiency of kaolin in absorbing toxins from kit. Example, efficiency of aluminum hydroxide, that is NaOH, as antacid. Blood plasma substitutes as dextrans, PVP and gelatin are hydrophilic colloids used to restore or maintain blood volume. Iron dextran complex form non-ionic hydrophilic salts used for treatment of anemia. Properties of colloids, that are kinetic, optical and electrical properties. Now we will study kinetic properties, which relate to the motion of the particles within the dispersion medium as follows, that are Brownian motion, diffusion, sedimentation, osmotic pressure, the Donan membrane effect and viscosity. Now Brownian movement. What is Brownian movement? Definition: colloidal particles are subjected to random collision with molecules of the dispersion medium, so each particle moves in irregular and complicated zigzag pathway. Now these are the irregular movement of dispersion medium, that is a solvent, so they are in a zigzag path. First observed by Robert Brown in 1827 with pollen grains suspended in water. The velocity of particle increases with decreasing particle size and viscosity. Increasing the viscosity of dispersion medium by glycerin decrease then stop Brownian motion. Okay, if the velocity of particles increases with decreasing particle size and viscosity. Now the increasing the viscosity of dispersion medium by glycerin decreases the stop Brownian motion, means the particles which are moving in a random way, it stops if we increase the viscosity of that solvent. Now diffusion. As a result of Brownian motion, particles pass, means particle diffuse from a region of higher concentration to one with lower concentration. Rate of diffusion is expressed by Fick's first law, dm upon dt is equals to minus dA upon dc upon dx. Where dm is the mass of the substance diffusing in time dt across an area A under the influence of a concentration gradient dc upon dt. The minus sign denotes that the diffusion takes place in the direction of decreasing concentration. D is diffusion coefficient. See, higher concentration to lower concentration. Solute. Transport is from left to the right. Movement of the solute is due to the concentration gradient. Next is sedimentation. That is Stokes law. V is equal to 2r square P0 G upon 9 eta. V is velocity of sedimentation of spherical particles. P is density of the spherical particles. P0 density of the medium, and eta is viscosity of the medium. G is acceleration due to gravity. At small particle size less than 0.5 micron meter, Brownian motion is significant and tend to prevent sedimentation due to gravity and promote mixing instead. So we use an ultracentrifuge which provides stronger force, so promote sedimentation in a measurable manner. Osmotic pressure. The method is based on Van 't Hoff's law, P is equal to RTC upon M from the equation. The osmotic pressure P depends on molar concentration of the solute C and on absolute temperature T. The osmotic pressure is inversely proportional to molecular weight M. Hence R is the molar gas constant. The equation is valid for very dilute solution in which the molecules do not interact mutually. The Donan membrane effect. Definition is the diffusion of small ions through a membrane will be affected by the presence of charged molecule that can't penetrate the membrane due to its size. Means diffusion of some small ions through a membrane will be affected. Means diffusion of small molecules through a membrane will be affected by the presence of charged macromolecule that can't penetrate the membrane due to its size. Application will be facilitating the absorption of ionizable drugs from GIT by co-administration of macromolecules of the same charge so mutual ionic repulsion occurs. Example, co-administration of anionic macromolecule, example sodium carboxymethyl cellulose, with a diffusible ion, example potassium benzyl penicillin, to enhance diffusion of the latter across body membranes. These are the diffusion coefficients. Next is viscosity. Definition is the resistance to flow of a system under an applied pressure. Viscosity of colloid allow calculation of the molecular weight. Second, provide useful information about the shape of the colloidal particles. Periocolloidal dispersion are of relatively low viscosity. On the other hand, linear colloidal dispersion area of high viscosity. If the linear colloidal particles coil up into spheres, the viscosity of the system falls due to the changing the shape. Next is optical properties, light scattering, that is Tyndall effect, ultra microscope and electron microscope. Light scattering, as we have seen in the last chapter, that is Tyndall effect. True solutions do not scatter light and appear clear, but colloidal dispersion contain opaque particles that do scatter light and thus appear turbid. Tyndall effect. When a beam of light passes through a colloidal source, scattered light causes the source to appear turbid. Importance of light scattering measurement, that is estimate particle size, estimate particle shape and estimate particle interactions. The Faraday-Tyndall effect. Tyndall effect. See, this is the Tyndall effect. Pointer traveling through a solution right and through a colloidal suspension left. This pointer is traveling through over here. These are the clear solution and this is suspension. Now, ultra microscope and electron microscope. Particles appear as spots of light against the dark background of the microscope, used in the technique of microelectrophoresis for measuring particle size. Give actual picture of the particles up to 5 angstrom, used to observe the size, shape and structure of souls. High energy electron beams are used, having great resolving power. One disadvantage is only dried samples can be examined, not given information on solution. Electrical power properties are electrical properties of interfaces, the electrical double layer. Electrical properties of interfaces. Most surfaces acquire a surface electric charge when brought into contact with an aqueous medium, the principal charging mechanism being as follows: ion dissolution, ionization and ion absorption. In ion dissolution, distributes and then it again ionization and ion is absorbed. Now ion dissolution, surface charge of colloidal particle is controlled by the charge of ion present in excess in the medium. Example is AgNO3 plus NaI give AgI plus NaNO3. Silver iodide in solution with excess iodide, particles acquire negative charge and vice versa. If excess Ag, the charge will be positive since the concentration of Ag and I determine the electric potential. Aluminum hydroxide in a solution with excess hydroxide, particles acquire negative charge and vice versa. Potential determining ions whose concentration determine the electric potential and the particle surface. These are the examples of potential determining ions. Now ionization step is surface charge of colloidal particles is controlled by the ionization of surface grouping. Example, polystyrene latex has carboxylic acid group and the surface ionized to give negatively charged particle. Acidic drugs as ibuprofen and nalidixic acid require surface negative charge. Amino acid and proteins have carboxylic and amino groups whose ionization depends on pH as follows. These are the amino group. At high pH, alkaline medium negatively charged. Deuterion means isoelectric point zero charge. Why zero charge and why it is called as deuterion? Because positive and negative charges are in the same molecule. Okay, at low pH acidic medium positively charged. See, at high pH it will be alkaline medium negatively charged, and at low pH acidic medium it will be positively charged. When NH2 will convert into NH3 plus, here COH will convert into COO minus. Pseudoionization, isoelectric point. What is meant by pH at which negative charges is equal to positive charges. That is, net charge of amino acid is 0. It is definite pH specific for each protein. At this pH is least soluble and precipitate. How can you precipitate insulin? By adjusting the pH of the solution to the isoelectric point of insulin. Which is pH 5.2. Ion absorption, surface charge of colloidal particle is controlled by the unequal absorption of oppositely charged ion. Examples are surfaces of sole in water are more often negative charged than positive charged because cations are more hydrated than anions, so cations reside in the bulk while less hydrated anion absorbed on the surface. The electrical double layer definition is development of a net charge at the particle surface affects the distribution of ions in the surrounding interfacial region. As a result, concentration of counter ions increase at the surface. Thus, an electric double layer exists around each particle. Example, AgNO3 plus NaI gives AgI plus NaNO3. Now, these are the AgI molecules and these are Na plus molecules and I minus. Okay, now these AgI molecules, I are minus charge, then the positive charge will attract minus charge. Okay, which will form a layer, and this is known as the electrical double layer of oppositely charged ions. Silver iodide salts can be prepared by their reaction. AgNO3 plus NaI gives AgI plus NaNO3. In the bulk of AgI particles, 1:1 ratio of AgI plus and I minus are observed. If the reaction is carried out with an excess silver nitrate, there will be more AgI plus than I minus ions in the surface of the particles, which will give the particles will thus be positively charged and the counter ions surrounding them will be NO3 minus. The combination of positively charged surface and the atmosphere of counter ions surrounding it is called the electric double layer. If the reaction is carried out with an excess of NaI, there will be more 1 minus I minus than Ag plus ions in the surface of particles. The particles will thus be negatively charged and the counter ions surrounding them will be Na plus. This is the end of our chapter.